In this presentation, we will discuss some of the relationships between water disinfection byproducts and increasing bromide concentrations in source water. This work was prepared in collaboration with Butts County by researchers at the University of Georgia, with financial support from Butts County and a regional water plan seed grant from the Georgia EPD. Disinfection byproducts, or DBPs, are compounds created unintentionally when halides, including bromide and iodine, and other pollutants react with natural organic matter, which is present in source water, with disinfectants during the drinking water treatment process. Around 700 DBPs have been discovered worldwide, but only a subset of these have been evaluated for risks to human health. Along with bromate and chlorate, the 11 regulated species of DBPs include trihalomethanes, which are referred to as TTHMS or THM4, and haloacetic acid, which are also referred to as HAAS or HAA5. There are also other bromine-containing haloacetic acids that are not regulated but are monitored as part of new EPA regulations, including the HAA6BR and the HAA9 rule. The following table from Cortez and Marco in 2018 summarizes the major classes of disinfection byproducts and their occurrence values. Disinfection byproducts are created when characteristics of source water interact with the disinfection process used by a given water utility. For example, during chlorination or disinfection with chlorine, bromide is oxidized to form hypobromous acid, which reacts with organic matter to form brominated DPBs, including bromoform, trihalomethanes, and haloacetic acids. Alternatively, during ozonation, hypobromous reacts with ozone to primarily form bromate. Thus, this suggests that depending on the type of disinfectants that are used and the characteristics of the source water, there are several processes that can create brominated disinfection byproducts. Bromide in itself is not a risk to human or ecosystem health when present in source water. The levels of bromide that are toxic to humans and other species are much higher than most natural environmental bromide concentrations. In fact, since natural background levels of bromide are so low in the environment, and this is an exception of seawater shales, coastal groundwater, and soils, bromide has been regularly used in environmental studies as a non-reactive tracer to study water and solute movement in soils and streams. In contrast, brominated disinfection byproducts formed when bromide reacts with natural organic matter and with chemical oxidants during the drinking water decontamination process may represent serious risks to human health. Across classes of disinfection byproducts, toxicological studies using a variety of methods have indicated that cytotoxic, neurotoxic, mutagenic, genotoxic, carcinogenic, and other consequences of DBP exposure exist. The following table from Richardson et al. In 2007 summarizes some of the toxicological findings for the regulated and unregulated brominated disinfection byproducts are particularly concerning because they are more carcinogenic than their chlorinated analogs in animal studies. It is important to note that a growing number of toxicological studies show that emerging disinfection byproducts containing iodine and nitrogen may be even more carcinogenic and cytotoxic than brominated disinfection byproducts, although they are typically present in finished drinking water at much lower quantities. Since the 1980s, several epidemiological studies have investigated whether exposure to DPBs in chlorinated water is associated with negative human health consequences, including cancer and effects on the reproductive system. There is consistent evidence from individual studies and meta-analyses of an association between urinary bladder cancer and DBP exposure, and this is typically measured as trihalomethane or haloacetic acid concentrations. It is important to note that a mechanism for trihalomethanes or haloacetic acids to contribute to bladder cancer has not been identified, and therefore the support for a causal relationship between trihalomethanes or haloacetic acids and bladder cancer is weak. Nevertheless, the consistent association of chlorinated water consumption with urinary bladder cancer is a cause for concern, and more research is necessary to identify the classes or species of DPBs driving this relationship. Several studies have looked for associations between DBP exposure and colon and rectal cancer, but results between studies are inconsistent, so this relationship is considered inconclusive. Further, recent critical reviews have highlighted methodological problems that limit the confidence in the findings of these studies. Studies investigating the adverse effects of DBP exposure, again typically measured as trihalomethane concentrations or haloacetic acid concentrations, on fertility, pregnancy, and fetal development have yielded inconsistent and controversial results. Similar to concerns regarding results that associate DBP exposure with rectal or colon cancer, the current links between DBP exposure and negative reproductive outcomes are inconclusive. However, there is some evidence of an association between THM exposure and fetal growth, specifically weight according to gestational age. Fertility endpoints that have been studied in response to DBP exposure include sperm quality and menstruation cycle length, but findings have been inconsistent. One study found an association between tap water consumption with THM levels greater than 75 micrograms per liter during pregnancy and an increased risk of spontaneous abortion. However, this finding has not been confirmed in subsequent studies with improved DPB exposure estimates. Brominated DPBs are created when bromide, natural organic matter, and chemical disinfectants react during drinking water decontamination. Although chlorine and bromine compete for organic reaction sites, bromine is more efficient at substitution. Natural organic matter is composed of humic acids, hydrophilic acids, and other compounds that vary in quantities both geographically and seasonally. The removal of natural organic matter prior to disinfection can reduce the overall formation of DBP formation, but when the source water also contains high level of bromide, increasing the bromide organic matter ratio can lead to proportionally greater brominated DBPs in the final water.